Buenas tardes. Good evening, everyone. My name is Giuliano Basso. I'm a PhD student from the Universidad Nacional de La Plata, and I'm currently working with the Grupo de Magnetismo y Materiales Magnéticos at the Instituto de Física La Plata, La Plata Physics Institute. So this is our group. We are from Argentina, the homeland of Leo, and we are in the beautiful symmetric city of La Plata, next to the Rio de la Plata river. This is our institute. So my presentation aims to describe our most recent results concerning magnetic nanoparticles, radio frequency cycles in different types of carrier media. So let's begin by discussing the magnetic nanoparticles. These nanoparticles are typically composed on iron oxides with possibly doping of other elements. And there are two key characteristics that make magnetic nanoparticles particularly intriguing for us. The first one is their size. Their nanometric size enables these nanoparticles to interact with essential biological structures, such as cells or organelles. The other main characteristic is their magnetic properties, which allow us to manipulate these magnetic nanoparticles using an external magnetic field, turning these magnetic nanoparticles into nanoactuators. So these two features underscore the potential of magnetic nanoparticles in biomedical applications. Our research group focuses on two types of applications based on the same principle. The magnetic nanoparticles absorb energy from the radio frequency field and release it as heat to their surroundings. So these applications are the magnetic fluid hyperthermia, which is a well-established complementary cancer therapy, which is based on the fact that increasing the temperature of the tissue to 41, 42 degrees Celsius can preferably kill tumor cells rather than normal ones. The other application is the nanowarming of cryopreserved organs perfused with magnetic cryopreservation agents. Here, the magnetic nanoparticles enable us to control both the heating rates and the heating uniformity, which is essential to avoid the tissue damage during thawing. So in these applications, the principle is the same. The magnetic nanoparticles absorb energy from the radio frequency field and release it as heat. The power dissipation has its origin in the magnetization lag in response to the applied magnetic field. This lag is characterized by the magnetization's relaxation time. We call it tau. So the key performance metric for this application is called specific absorption rate, and it is the power dissipation per unit mass of magnetic nanoparticles at a specific field amplitude and frequency. The SAR of the SAR value, SAR, specific absorption rate of the set of magnetic nanoparticles depends not only on the field parameters, but also on the supporting medium and the spatial distribution of the nanoparticles, which influences dipolar interactions between them. We use the electromagnetic approach in order to obtain the radio frequency cycles of magnetic nanoparticles. This is a picture of our setup, and this recently developed technique is based on the inductive measurement of the electromotive force generated in a sensor coil pair by the time derivative of the sample's magnetization. What's interesting here is that for systems with an antisymmetric response concerning the direction of the applied field, and for those whose dynamics are determined by the Giuliano relaxation equation, we have found that the specific absorption rate and the relaxation time depends solely on the magnitude and phase of the first harmonic of the response signal. So now the specific absorption rate, we define it in this way, where this factor is the area in this hysteresis loop, and we take into account the frequency of the field and the concentration of the magnetic material. So here are some of our results. During our research, we successfully measure radiofrequency magnetic cycles of magnetite nanocubes in different carrier media. Aqueous-based liquid suspension, let's see here, and an epoxy resin solid suspension, where we can see big differences in the frequency spectrum. Again, the information which is relevant for us, the specific absorption rate and the relaxation time, is in the first harmonic of the signal. Additionally, we conducted measurements of the radiofrequency cycles of citrate acid-covered magnetite nanospheres suspended in an aqueous-based solution. These measurements were taken during the process of thawing the carrier medium from cryogenic temperatures to the room temperature. So we can show here the relaxation time and the specific absorption rate for the temperatures. And we can see that the biggest differences in the cycles occur here in the solid liquid transition zone. So, conclusions, yes, very quickly. In both systems, we were able to directly determine the specific absorption rate and the relaxation time. As far as we know, no other research group has reported measurements of this kind. And due to its simplicity, we envision significant potential in implementing this groundbreaking approach in future experiments. Thank you for your attention. Muchas gracias.
Thank you, Giuliano. Floor is open for questions. If you have any questions, you can also use the chat box. Yes. I don't see any questions here, so we can move forward. Thank you, Giuliano, for your time.